In 2019, fire destroyed Notre-Dame's timber roof, toppled its spire, and punched through parts of the medieval stone vault below. Yet much of that vault remained, 33 meters above the floor, spanning a nave whose walls were opened for glass. There was no modern steel frame inside. But this was not metal-free. Medieval iron staples were hidden between some stones. The builders wanted three things that fought each other: greater height, larger windows, and less masonry holding everything together. Stone can carry enormous compression.
Bend it, pull it, or let its joints open too far, and it begins to fail.
An arch does not send weight straight down. Each wedge squeezes its neighbor, creating a force that also pushes outward. The pointed arch reduced that horizontal thrust and gave masons more control, but it never removed the sideways force completely.
Extend arches through space, cross them, and a ceiling becomes a three-dimensional shell that channels weight towards selected supports. The ribs mattered, but they did not carry a passive ceiling alone. The stone web between them also shared the load. At each bay, vault weight gathered near the springing, where upper masonry had to resist a persistent outward thrust.
The flying buttress carried that shove across open air, transferring it from the high wall toward a heavier outer pier.
The outer pier, sometimes loaded by a pinnacle, kept the combined force inside masonry instead of letting the support overturn. Every elegant line ended in something invisible: foundations and soil. If they settled unevenly, the geometry above had to change. The vault was not the only load. Wind struck the high walls, while the timber roof added weight and lateral forces.
Small cracks let joints open and forces redistribute. A damaged cathedral could find another compression path, until movement went too far.
Before the vault could support itself, carpenters built a second cathedral of timber: centering, platforms, wedges, ropes, and scaffolds. Full-scale curves, templates, plumb lines, and marked stones turned geometry into instructions that hundreds of hands could repeat accurately. These cathedrals survived through geometry, redundant load paths, hidden iron, controlled movement, and generations of repair. How can loose stones carry themselves?
A stone joint can open by less than a millimeter, yet the arch above may remain standing.
Remove the mortar entirely, and accurately shaped blocks can still stand, because gravity presses every voussoir against its neighbors.
At every joint, compression creates contact and friction, preventing neighboring stones from sliding freely past one another under load.
Engineers represent that hidden chain of compression as a thrust line running through the thickness of the arch.
The stone may be far from crushing. Failure begins when geometry drives that thrust line too close to an edge.
If the thrust line stays inside masonry, every joint can carry compression, even while a visible crack remains open.
When one joint opens, contact shifts to another part of the stone. The crack begins behaving like a hinge.
More than one hinge may form while the blocks still find a balanced compression path between the supports.
But once enough hinges align, the arch becomes a mechanism. The stones can rotate instead of carrying load. A support moving outward can create those hinges long before the limestone itself approaches its crushing strength.
In this equal span comparison, the rounded arch followed a flatter path and demanded a stronger horizontal reaction at the supports.
With the same and comparable load, raising the crown steepened the compression path and reduced the outward reaction.
That advantage was not magical or universal. Span, rise, thickness, loading, and support conditions all changed the result.
Masons shaped wedge-like voussoirs and radial joints, so neighboring stones met cleanly along the intended curve.
Mortar evened imperfect surfaces. It was not modern glue. One arch solved one slice, but a vault had to cover a room. Mortar was not modern glue. Subscribe to Lantern History. Next, one arch becomes a vault above empty air.
One arch could cover a narrow slice. Crossing it with another created the first geometric framework of a vaulted bay. Diagonal ribs connected opposite corners, fixing the bay's principal curves and giving masons durable guides above the empty room. Before those ribs could carry compression, each curved line had to rest on precisely shaped timber centering during construction. At the crown, carefully cut crossing stones joined the ribs, but the whole vault, not one keystone, created stability. Near the springing, several ribs merged into dense masonry, concentrating weight where the wall and pier could receive it. Masons closed the spaces between ribs with lighter web masonry, laid in courses whose exact patterns varied by workshop. Each course curved in more than one direction, turning small stones into a shell that could carry compression through space.
The web did not hang from ribs like fabric. It formed active masonry, carrying compression through several possible routes.
Under one geometry, the web carried more. After settlement, ribs could attract different loads. The distribution was never fixed.
Rubble and mortar above the lower vault could stiffen the springing and redirect thrust, making hidden fill structurally important. Models suggest ribs could reduce stress concentrations near supporting piers and stiffen the vault, though greater stiffness could sharpen cracking.
Notre-Dame's early high vaults divided each double bay into 6 cells, using an intermediate transverse rib within the crossed system.
Repeated bays were never perfectly identical. Masons adjusted profiles, curvature, and joints to walls that were not perfectly square. When centering was lowered, masonry settled, joints closed or opened, and temporary wooden geometry became a permanent compression system. The finished vault offered gravity several routes toward the springing, but every route still pushed outward against the upper wall. The upper wall could not absorb every sideways thrust alone. Builders connected it to a second support beyond the aisle. Without that connection, the vault's outward reaction could rotate the slender upper wall and widen cracks around its openings. A flyer worked best when its upper contact met the wall near the zone where vault thrust arrived. The flying arch was not a tie pulling inward. Its stones carried compression across the gap toward the outer pier.
Changing a flyer's angle, curvature, thickness, or contact height redirected compression through the masonry and altered support behavior.
At the far end, the force entered a massive buttress pier designed to resist sliding, rotation, and concentrated compression. A pinnacle could add useful vertical weight, drawing the combined force deeper inside the pier, but its contribution varied. No two buttresses carried identical loads. Actual geometry, cracking, roof forces, and settlement changed how each support behaved.
The pier was only stable if its foundations that force into soil without excessive settlement or outward rotation.
Together, vault, wall, flyer, pier, and foundation formed one transverse frame, a continuous route from ceiling to ground.
Some cathedrals added several tiers of flyers. Their roles differed, and researchers still debate certain upper connections.
Wind pushed across clerestories and roofs, so the exterior skeleton also had to resist forces that changed direction. Above the vault, the timber roof carried its own weight and wind reactions into walls already balancing stone thrust. Drainage mattered too. Water entering joints could damage mortar, corrode iron, split stone, and weaken repairs over centuries. For more evidence-based engineering history, subscribe to Lantern History. Next, we reveal the timber cathedral hidden beneath the stone.
A small wedge adjusted one section of centering, yet millimeters below precisely controlled the stone curve high overhead. The circle was their primary tool, used to derive every proportion without a single written digit. Wooden templates carried that geometry from the floor to the mason's bench, defining the exact shape of every joint. Assembly markings, a secret language of position, told the workers exactly where each block belonged in the sky. Each ribstone solved two geometries: longitudinal position along a curve, plus the carved profile visible from below.
Construction lived on a lattice of oak. Masons worked 30 meters up on platforms secured by nothing but knots and skill.
To lift the mountain, the builders harnessed the circle. The great treadwheel was the engine of the high Gothic. A hoist raised each block, while workers controlled its final meter: rotation, alignment, contact, and danger above the nave.
Every fiber was tested. Mechanical advantage turned human labor into vertical height.
The stones made a slow, silent climb, reaching coordinates determined years earlier on the tracing floor.
There was no margin for error. A single slipping knot or a miscalculated shift could be fatal. Above the stone, a second cathedral was built of wood. Thousands of oak trees formed the massive roof forest.
This timber shield was armored in lead, protecting the drying vaults from the relentless rain of Paris. No single genius built this cathedral. Coordinated workshops, materials, payments, records, repairs, and changing masters transformed geometry into stone.
The timber cathedral is gone, but its geometric logic remains, locked in the stone, standing for 8 centuries.
The timber vanished, but its evidence survived. Subscribe to Lantern History. Next, science puts Notre-Dame under the microscope. Notre-Dame stretched roughly 127 meters, while its central nave spanned 13 meters beneath vaults rising 33 meters.
Its early high vaults were sexpartite, 6 masonry cells spanning double bays, with real geometry that varied from bay to bay.
Researchers combined laser scans, masonry observations, historical drawings, and physical experiments to reverse engineer how these unusual vaults were planned and built. A scan records surviving shape, cracks, and deformation. It cannot reveal one unique medieval force path or every lost construction detail.
On 15 April 2019, burning roof timbers and the falling spire struck the vaults from above with concentrated force.
Some bays collapsed, while much of the medieval vaulting remained. Survival was substantial, but the stone ceiling was never indestructible. From one fallen transverse arch, researchers recorded 79 voussoirs. Most could be identified, and 71 entered detailed analysis. Thickness, carved marks, centering notches, recovery position, and stone geology helped match fragments, but only a few placements were certain. On the ground, the arch was assembled without mortar. Each uncertain stone tested a reconstruction rather than proving the original sequence. A digital twin linked scans, recovered stones, locations, and alternative assemblies, allowing physical and digital reconstructions to challenge each other. Engineers also compared continuous masonry models with block-by-block simulations, because no single method captures every feature of damaged vaults. The fire also opened access to wrought iron staples hidden between stones in galleries, aisles, and the cathedral's upper walls. 6 sampled staples were radiocarbon dated to medieval building phases, making Notre-Dame the first known Gothic cathedral with such extensive iron integration.
Metallography revealed welded, heterogeneous iron from multiple supply sources. It bound masonry, but its exact structural contribution remains uncertain. If this evidence-based reconstruction changes how you see old buildings, subscribe to Lantern History. Next, 8 centuries of movement and repair.
800 years of survival was not a state of frozen perfection. The building moved as soon as it rose. Rainwater found every imperfect lead joint, seeping into the masonry core to dissolve ancient lime mortar from the inside. Gargoyles and channels were critical weapons against decay, carrying corrosive moisture away from the vulnerable limestone walls and foundations. Trapped dampness reached the hidden iron, causing rust to expand and shatter the very stone it was meant to secure.
As iron corroded, expanding products pressed against surrounding limestone, sometimes splitting the masonry originally meant to remain connected.
Weathered blocks were cut out and replaced, weaving newer limestone into the medieval fabric to preserve the structural circuit. Stewards monitored leaning piers with plumb lines, recording the slow, tectonic shifts of a cathedral settling into its environment.
The 19th century brought massive interventions, replacing entire flying buttresses and pinnacles to stabilize the shifting high Gothic skeleton.
Craftsmen carved fresh voussoirs using traditional tools, ensuring the replacement stone shared the same geometric logic as the original.
Upper vaults often leaked, requiring constant inspection of the roof forest to protect the masonry shells from frost damage. New iron ties were sometimes added to brace arches, creating a hybrid system of ancient craft and industrial-age reinforcements.
Today, digital sensors track movement to the micron, continuing a maintenance ritual that has never truly stopped since 1200. At Beauvais, builders raised the choir vault to nearly 47 meters, stretching Gothic height, lightness, and slenderness beyond earlier precedents.
The choir was not one seamless design. Interrupted campaigns introduced misalignments and structural adjustments into an already daring geometry. Broad bays, slender intermediary uprights, and extremely tall outer buttresses reduced the safety margins for small geometric errors or shifting forces.
The finished vaults stood for nearly 12 years, suggesting that vulnerability alone was not necessarily the final trigger.
Scholars have proposed misalignment, unstable supports, wind, local breakage, and long-term mortar deformation. No single explanation has won agreement. Any trigger could shift the thrust path, open several joints, and turn a stable vault into a rotating mechanism.
On a November evening in 1284, sections of the choir vaults fell, breaking supports and shattering clerestory windows.
The curved hemicycle remained largely intact, and roof timbers survived damage, evidence that failure was severe but not total. Rebuilders inserted fresh intermediate piers, dividing 3 broad bays into 6 while replacing quadripartite vaults with sexpartite ones.
Rebuilders rejected the failed scheme, shortening spans, adding supports, thickening masonry, and deliberately redirecting load paths through new piers.
For medieval builders, collapse itself became evidence. Dimensions, sequences, and supports were revised through observation rather than modern calculation.
Beauvais tested the limit again. An enormous tower completed over the crossing in 1569 collapsed only 4 years later.
The cathedrals before us are survivors, often repaired, reinforced, altered, or rebuilt after weaker experiments failed or disappeared.
They endured not because stone was indestructible, but because enough compression paths were preserved, corrected, and repaired across generations. Stone survived because geometry guided gravity, and generations preserved the path. Thank you for watching Lantern History. Subscribe for more evidence-based history.